previously we had developed some rules for how the electric field and how charge behaves on a conductor. And what I would like to do now is come up with one more rule that has to do with the potential of a conductor. Okay, so recall that we had that the electric field has to equal 0 inside a conductor. So we had a couple of different explanations for why that was the case. One was that if the electric field wasn't 0, then it just wasn't in equilibrium yet, and so we just wait until it is. The other is that conductors quickly come to equilibrium because the charges move in response to any external electric field until the electric field goes to 0. For similar reasoning, we found that the electric field outside a conductor is perpendicular to the surface. And again, the exact same arguments made us come to that conclusion. And then our final conductor rule is that excess charges move to the surface. And we explained that in terms of Gauss's law. So if we draw a Gaussian surface just inside the surface of the conductor, in order for the electric field to be 0 everywhere, there needs to be no charge enclosed by that surface. So all of the charge has to go to the very outside of the conductor. So we can actually use those ideas to figure out what is going on in terms of the potential in a conductor. So what I'm going to do is sketch a conductor like so. And the electric fields for a conductor are going to look kind of like this. Perpendicular at the surface and then kind of spreading out as it moves away. Like so. But E equals 0 inside. Alright, and what that means is if I pick any 2 points inside the conductor and I integrate the electric field along some path connecting those 2 points, I'm going to get 0 because the electric field is 0. So the difference in potential then between any 2 points in a conductor is 0. What does it mean if the difference is 0? It means that they're at the same potential. So any 2 points in a conductor are at a constant potential. So our new rule then is a conductor is at a constant potential. And if you want to think about what that means in terms of the hill analogy, well, we're going to essentially have some sort of hill with a flat top, like this, and then the elevation of the hill is going to change gradually as you move away. Okay, so here the elevation is not 0, but the elevation is constant. And then we can see that the electric field points away at different outward positions here. So this is actually going to be really, really important when we're studying electric circuits because electric circuits are built out of conductors. And so one of the rules that we're going to use over and over is that any wire or any other conductor that is connected to other conductors has to always be at some constant potential. No matter how complicated the network is, anything that's just connected conductor to conductor is at a constant potential.